I love all those topics, and the challenge I have is I get so excited that I just start talking and talking and talking. See if
I
I
think
can.
we all share this. I mean, it's so nice,
Yeah.
really exciting times.
Okay, it's our great pleasure to interview Amin Vahdat today. So Amin is an engineering fellow and vice president for machine learning systems and cloud AI at Google. In the past, he was also professor of computer science and engineering at UC San Diego. Amin is a fellow of ACM and recipient of many prestigious prizes, including SICOM Lifetime Achievement Award, and also many Test of Time awards. So thanks a lot, Amin, for joining us today.
It's my tremendous pleasure. I've been really looking forward to this discussion.
Thank you very much, Amin, for joining. Maybe we'll start by you telling us a bit about your background, how you become involved in data center network, and more lately in a reconfigurable data center network.
Yes, some good memories. My background has always been in systems, originally operating systems, and then distributed systems. And actually, I remember it was probably almost 20 years ago where I was serving on a review panel organized by Microsoft, actually. And one of the problems that they identified was bottlenecks in their large-scale distributed systems with their networking. And essentially, they couldn't get, and this was, I learned, common, not just restricted to Microsoft. Most companies, so-called hyperscalers, I don't think they were called that at the time, in building their next generation services. Think of this as the, maybe, I won't say the golden age of distributed systems, but in the early mid-2000s, think of systems like GFS or Bigtable, Hadoop, if you want, from an open source perspective. Many of these ran in a scale-out manner on thousands of servers. And of course, partitioning the tasks with lots of communications. The network was a bottleneck, essentially because most people were taking internet scale systems, routers, and putting them into data centers. Right? And of course, internet scale bandwidth, where at the time, certainly humans were principally in the loop, right? And the amount of bandwidth that was required, this was pre-large scale video and interactive gaming and things like this was modest. So if you try to take those systems and then retrofit them to data centers, you wound up with lots and lots of commodity servers, so scale out, and plentiful compute, lots and lots of, at the time, disk, later SSD, so plentiful storage. But the network was the bottleneck. So a number of us, I was a faculty member at UC San Diego at the time, a number of us started thinking about the problem of how we could bring the necessary bandwidth into the data center while leveraging some of the same paradigms of scale out. And really what this meant then was to consider topologies that were amenable to scale out, while also simultaneously taking advantage of commodity switch silicon, which was at the time becoming commonplace. So in other words, rather than necessarily going to high-end internet router vendors to build out your data center network, could you take advantage of emerging commodity switch silicon? And at the time, I remember bleeding edge at the time was 24 ports of 10 gig, right? Which would be tiny right now. I mean, we're at a level of, I don't know, 64 ports of 200 gig, 400 gig, etc. So this was a while ago, but the amazing thing is the principles don't change. And I then, this is why it's so important to have, I guess, a complete graduate student level education. I remembered my course on distributed computing and supercomputing, and the fact that MPPs like thinking machines and others took advantage of different topologies, and in particular CLO topologies as a starting point for how to scale out networking. And again, since we have a relatively limited amount of time, we won't go into all the details, but essentially the beautiful thing was that you could take commodity switch silicon, relatively inexpensive, and arrange it in a hierarchical topology to deliver non-blocking bandwidth among servers. So in other words, if the server NIC at the time, bleeding edge, was 10 gigabits per second, of course much higher now, you could take these same 24 port 10 gig switches in a 3-level, 4-level, 5-level hierarchy and deliver non-blocking bandwidth to them. And so that was, to me, a fascinating opportunity. And so we wound up building some prototypes around this at UC San Diego. And of course, companies were investigating similar approaches as well, contemporaneously. And systems like VL2 out of Microsoft, really nice work there, and others were happening in parallel.
So on a high level, what are the main design goals of current state-of-the-art data center networks?
Right, exactly. So one of the things that we were able to achieve was essentially, after a few iterations, was getting to the point where, let's say, a data center building might consist of approximately plus minus 50,000 servers. Could you get to the point where you could deliver non-blocking bandwidth among those 50,000 servers? So whether it was 10 gigabits per second, later 40, 100, 200 gigs, and growing from there.
Can you explain in one sentence what you mean by non-blocking?
Yeah, great question. So I think and this is a really important point. The definition here is the bisection of the network should be the product of the link bandwidth, let's say 200 gigabit per second today, times the number of server elements, endpoints. Right, so I won't try to do the math in real time, but if you have 50,000 servers, each with a 200 gigabit NIC, a non-blocking network is such that the bisection will have 50,000 times 200 gigabits per second of aggregate bandwidth. What this means is that for arbitrary adversarial traffic patterns, you can come up with a schedule of placements of the traffic across the network such that everybody can talk to everybody else at full speed, irrespective of the communication patterns. So in other words, what this also says is that the network is rearrangeably non-blocking such that as new traffic arrives, in the face of an adversary, again, pick the worst case communication patterns. And you can imagine for a tree, it would be with a single root, it would be everyone trying to talk to everyone else on the other side of the tree as an adversary. Let's say, omniscient scheduler could come up with a schedule, a placement of the traffic to still support this non-blocking characteristic. Now, there's a lot of details, and I didn't get every sort of vocabulary perfect, but lots of great papers and books written on this topic. But the beautiful thing from an application perspective is, if you are a service running on a server, you don't have to worry about where your endpoint is. Right? And so from a placement and job scheduling perspective, if you're a 50,000 node job, awesome. Like everybody can talk to everybody at full speed. Now, those are actually pretty rare. Not impossible, but let's put aside machine learning, large-scale machine learning training for a moment. So that's, of course, been a really important workload recently. Previously, it wasn't so much that you needed to have 50,000 node jobs. It was maybe you had a lot of 1,000, 2,000, and 4,000 node jobs. Wouldn't it be nice from a bin packing and scheduling perspective if you can place them anywhere without having to consult the application developer? And we've actually done some studies at Google on the cluster scheduling side in a system called Borg. There's a Eurosys paper that highlighted this, that shows that by being able to not have to think about the network, you could get substantial 10%, 20% efficiency gains, or more in some cases, in cluster utilization, server utilization. So the point here is that by allowing the network to get out of the way, quote unquote, get out of the way, the more expensive compute becomes more efficient. Right? In other words, the network should be actually a relatively small fraction. Rule of thumb might be 10% of systems cost. So, but if you can make the network be 11% rather than 10%, but then get 20% better utilization out of your expensive servers, that's an awesome trade-off. So, starting point answer was initially, and this is not necessarily because of the state of the art, the goal was to deliver this non-blocking, rearrangeably non-blocking network capacity at pretty massive scale, let's say 50,000 servers to the data center network. Let me pause there. I didn't actually answer your question about state of the art today because it's a little bit different, but let me make sure that makes sense.
So that sounds almost perfect. I mean, you cannot, it seems they cannot do better than that. So what are the disadvantages of this type of topologies?
Yes, great question. So one would think that it were perfect and we would be done. So I think that there are a number of possible concerns. A starting point is that these topologies required a full build out ahead of time to support this rearrangeably non-blocking nature in the, let's say, baseline mechanism for building it. So essentially what you would need to do, because of the, and again, we could go into the details, but assume that you have to have a 5-layer topology. 5 layers of switches. And across each of these layers, you would need the bisection of the network, essentially. So the wiring for this is very involved, intricate. And we're talking about multiple football fields, US football fields, that this would cover. Okay. So you can't say, well, on day one, I'm going to have 5,000 servers. So I'll just have a 5,000 port switch, logical 5,000 port switch, right? You actually would need to deploy almost the entire things without the TORs, possibly. The top of rack switches you could deploy late, but then the other, let's say 4 layers, if it were a 5-layer topology overall, would have to be pre-deployed. That's a substantial undertaking. And even if the network as a whole were cheap compared to the system, at full deployment, that's a big upfront cost, but it's also a substantial cost from the perspective of time to turn up. Remember that we want to turn these data center buildings up quickly. If a prerequisite for doing so is to have a complete 50,000 port logical network, that just, I mean, just the human labor. I begin to try to imagine how many boxes have to be unboxed, how many fibers have to be plugged in, cleaned, tested, etc. There's a speed of light here. That's part one. But now let's say that we can take care of all those issues. What happens when those servers need to be upgraded from 10 gig to 40 gig to 100 gig? The default answer is, okay, you have to turn down the entire building, like burn down the data center network, and replace that 50,000 port switch. Let's say you were at 10 gig with 40 gig. Okay, now 40 gig is done, and then you have to burn it all down and go to 100 gig. Not a satisfying solution, right? Time, now you're telling 50,000 servers and potentially thousands of customers, whether cloud customers or internal customers, hey, vacate the building for, you pick a number, 3 months, 6 months, while we put in the new network. Not a very satisfying answer.
Right. So how can reconfigurable topologies help here?
Yeah, so reconfigure, and let me just also put a couple more problem statements on the, I'll go through these next two more quickly. Latency is in the end a consideration. So while many applications aren't sensitive to latency and they just care about getting the bandwidth because maybe they can live with data center latency, others, especially high performance computing and machine learning, do care about latency. That's problem number 2. I talked about the pre-build as being problem number 1. Problem number 3 is reliability. Inevitably, at the scale of 50,000 ports and tens of thousands of switches and hundreds of thousands of links required to deliver this, every day you're having some component fail. Maybe it's a switch, maybe it's an optical transceiver, etc. So this is commonplace. So how do you deal with failures? So 3 key issues: incremental build-outs and upgrades, latency, and fault tolerance. And reconfigurable networks help with all 3 dramatically. So now essentially imagine that if I wanted to have a 50,000 port switch capable, I can actually start with a topology that quote unquote seems to max out at 1,000 ports. And I can pay as I go or deploy as I go, if you will, and incrementally deploy the network as I need, keeping up with the servers. So the time to turn up a building is determined by getting some modest number. I mean, obviously 10 servers is probably not enough to get a building up, but maybe 1,000 is, and you don't have to go all the way up to 50,000. And the network can be moving in parallel. More importantly, reconfigurable networks, assuming that they're built from optical circuit switches as a starting point, but they don't have to be. They can be configured to communicate with one another at different speeds. So in other words, if I have 2 switches and a new one comes in, let's say I have an existing 100 gig network that I want to upgrade to 200 gigs, new 200 gig switches are backward compatible with 100 gigs. And we can make sure that, and actually a key requirement here is to design your transceivers such that they can be. And I believe that you've spoken to others about the optical issues that come up here. But this is doable if you're taking it as a design consideration, such that my 200 gig transceivers are fully capable of communicating with 100 gig transceivers, are capable of communicating with 40 gig transceivers, and then forward with 400 gig transceivers in the future. Now I can have heterogeneous networks. I don't have to say, hey, it's going to be a 50,000 port, 10 gig, 40 gig, 100 gig, 200 gig switch, logically. It can have what we refer to as super blocks. And for us, this is typically on the order of 500 ports as a unit of deployment, which is a nice small size. It's not 50,000, right? So not enormous. It's not 10, but it's this rough unit of 500. And that is the unit of homogeneity. Within a quote unquote super block, you can go at 200 gigs, 400 gigs. But now you can deploy these incrementally, and they can be backward and forward compatible with other super blocks in the same building. So you can imagine sort of a rolling stripe. You can first deploy your 10 gig network, and then on top of it, you can deploy your 40 gig network. On top of that, you can deploy your 100 gig network, and it's block at a time, 500 ports at a time. And we never have to tell all services, hey, get out of the building for the next 3 months, right? All we have to do is have enough buffer to manage 500 servers worth of, let's say, drain at a time, right? You can imagine out of my 50,000 ports, I'm going to drain 1%.
Okay.
Do the upgrade in place and continue. So hopefully that answers the question of how reconfigurable networks help with the first problem. And I can get to the second and third, maybe relatively straightforward as well. Now with latency as a consideration, I can potentially short circuit my 5-layer topology. And so essentially, if, again, I benefit from a whiteboard, and we have papers on this that people can look at if they're interested, but imagine that I can flatten my 5-layer topology to be a 3-layer topology. And that's the level of a super block. And essentially, these 3-layer topologies can be directly connected to one another in a programmable fashion, such that those super blocks that happen to be hosting the same job, especially jobs that are latency sensitive, now don't have to have 9 hops worst case, right? And a 5-layer topology, again, you can imagine it's tree-based. It would be 9 hops back and forth between servers. It might get down to 5 hops, actually, which is meaningful in terms of latency reduction, all by creating the right topology in a reconfigurable manner between the servers. And then finally, for fault tolerance, once again, one can imagine, and this has been absolutely critical for our machine learning workloads, but also for our standard workloads. In response to individual failures, you can essentially create topologies that heal, such that you maintain the necessary bisection among different elements in the network. And all this requires, of course, a reconfigurable network, and one that responds in real time to communication patterns.
This is very interesting. I want to follow up. You mentioned some of the stuff, but to put things maybe a bit in perspective, can you tell us a bit about the journey from the seminal work about Helios that, I mean, maybe started this thing up to the current state of reconfigurable topologies that you use in Google Datacenter, and you published, for example, in the Jupyter Evolving paper?
Yes, I mean, it's been, candidly, one and sincerely, one of the highlights of my career. So in other words, what we were able to do is observe. We did have CLO-based topologies, and we deployed them at Google for a number of years, but we were able to observe some of the opportunities and benefits, especially from a life cycle perspective. Really, this is around the incremental deployability. I mean, the pain that customers, internal customers and external customers had to manage in terms of moving in and out of data centers in response to the network needing to be upgraded was actually substantial. So we were able to make a strong case for a reconfigurable network topology, not necessarily based on some of the more traditional considerations of latency and fault tolerance and even cost. So the other thing I didn't mention that's highlighted in our Jupyter Evolving paper is that actually the optical network is substantially cheaper than a traditional electrical network, because we essentially cut the number of stages from 5 to 3, and much less power consumption as well, because optical circuit switches require almost no power compared to electrical packet switches. The optical circuit switches, especially the MEMS-based ones that we use, are essentially reflecting light, and the only power required to run them is the power required to hold the mirrors in place in 3D. These are tiny, tiny mirrors, almost no power. So cost was substantially lower, power was substantially lower, but in the end, candidly, in an industrial setting, the benefits in absolute terms were too small to justify moving to a radically new network technology by themselves. In other words, we could say, hey, I'm going to take 10% of my systems cost and make it, I'm making it up, make it be 7%. And that's good, right? But it wouldn't be enough given the complexity, because essentially it required invention of a new technology that hadn't ever been demonstrated at scale and reliability before, and that was optical circuit switching. It also required substantially more complex routing and control systems relative to standard internet protocols, which were still the dominant ones for running data center networks. So the other part of the journey that I didn't talk about, and actually we could talk for another 30 minutes on it, is the control systems and the software required to make reconfigurable networks work. I mean, frankly, that's from a person like myself coming from a distributed systems background, that was a ton of fun, equal amount of fun, I would say. But so the journey really involved making the case for, and the, imagine, if you will, case for reconfigurable networks. And the basis for that was actually managing the life cycle of the buildings. Once we were able to do that, that's when we were able to go after some of the more advanced cases over the past few years, including latency, and including actually supporting machine learning with our TPUs and fault tolerance. And essentially all this came down to more and more real-time understanding of traffic matrices, and being able to do traffic engineering in response to communication patterns. Whereas you could imagine the sort of building time expansion was more at the level of days and even weeks in terms of reconfiguration. So the other important aspect of it here is that these control systems can suffer failures, like we can have bugs. The blast radius from such bugs is substantial. So the nice thing about our journey was we were able to start with a simpler problem from the perspective of distributed systems control, and then work more toward, okay, from weeks to days to hours to minutes to seconds. And once you get down to second level granularity, right, I'm responding, and ideally we get down to milliseconds and microseconds as well. That's next in terms of future challenges. But we were able to take a much more incremental path.
One follow-up question that I'm really interested in. We talk about the paper on demand aware compared to demand oblivious, and you mostly talking here about the topology that is demand aware. Can you say something about this demand oblivious, RotorNet, and other types of topology that are oblivious?
Yeah, so the starting point actually, and where we started even with our reconfigurable networks, was demand oblivious. So in other words, we still built 5-stage closed topologies with a layer of optical circuit switching that were demand oblivious and were rearrangeably non-blocking in response to arbitrary traffic patterns. And then even for the starting point for what we call direct connect topologies that eliminated the spine, were also demand oblivious. So in other words, we built in worst case 2-to-1 oversubscription for permutation traffic. It's really more recently that we're performing real-time, essentially what I call topology engineering to match communication patterns. Now, if you're being demand oblivious, there are different topologies. So then the nice thing about reconfigurable topologies is they're agnostic to whether you're being demand aware or demand agnostic. And you can create topologies that are better suited for arbitrary, quote unquote, communication patterns. Or you can be more aggressive and say, I'm going to rearrange my topology, my logical connectivity among the nodes in response to the communication patterns.
Welcome back, Amin. So let's continue. I would like to know a bit more about the challenges in the control system required for these reconfigurable data center networks.
The challenges on the software side, the control side, are as large or even larger, honestly. In other words, the topology, the hardware, all really exciting and interesting. But I think that in a network system, when we're talking about really making decisions at the lowest level at the granularity of nanoseconds. Now that's not going to necessarily be required, but microseconds for control is ideal. Ideal might not be required either, but certainly when you'll need milliseconds, certainly you'll need seconds. Our distributed system software structures by default aren't used to actuating, exerting control at that granularity. So actually the structure of how you collect information in real time about the state of your network, we want to just take simple examples like load balancing. How would you actually, in real time perhaps, for your forwarding decisions, your routing decisions, be able to pick which set of paths are well utilized, highly utilized, congested, perhaps suffering a failure, and react to it appropriately. As we all know, internet routing protocols by default were built for ensuring connectivity, not necessarily bandwidth or latency. And of course, that was the primary consideration. How do you make sure that there is a path from source to destination, not necessarily a path that is maintaining target levels of bandwidth and latency? So you could try to put all that functionality into hardware, of course, but then the hardware becomes very, very complex and perhaps untenable. Putting it into software is appealing, but now you're talking about control systems that have to collect state at really, let's say, microsecond granularity, and even actuate, which means programming the hardware, reacting to it in real time at the granularity of ideally microseconds. Maybe that's too hard, so milliseconds and seconds.
What do you think is the vision? This is toward distributed system, or there is still some role for centralized approach?
This is the question that doesn't have a right answer. So, I mean, I think the simple answer is yes. There's absolutely a role for both. And so I think that it's the partitioning that is the most interesting here. In other words, there is going to be a centralized component. On the other hand, the latency to the centralized component might be long. The fault tolerance characteristics of the centralized component might be less than ideal. Right? In other words, just again, when we're talking about ideally reacting in microseconds, you don't have time to get from your switches, collect the telemetry, get to the centralized controller, let's say physically centralized, if not logically centralized, do some computation and then respond. That's not a microsecond granularity, and maybe not even a millisecond granularity operation. So now how would you partition your responsibility? How would you install enough state from a centralized controller such that locally you can make good decisions, maybe not optimal ones. And then you can be updated in the background with optimal decisions at some coarser time scale. So I think the exciting direction actually is probably a hierarchy of controllers, with the leads being the individual switching elements.
All right, thank you.
Okay.
You mentioned earlier machine learning, so maybe you can elaborate a bit about the opportunity of reconfigurable network in the area of machine learning and large language models.
Right. So today we're co-designing our models with our hardware. So in other words, you can imagine that these models are very large, very complex. They, of course, as we know, don't fit on a single chip or server, right? Whether it's a GPU, a TPU, or something else, they have to be partitioned across thousands of elements. And now, how do you? Now your model consists of potentially dozens, if not more, layers, and billions of parameters. The mapping of these layers and parameters to the hardware is very, very interesting, because you want to do that mapping in a way that observes communication patterns. So for example, just taking one example, direction that's been very exciting recently has been mixture of experts. Here we have one large model that is made up of a number of, let's say, smaller individual experts, right, that get trained somewhat independently, not fully independently, but somewhat independently. The communication patterns among individual experts within this larger model might be more intense than between the experts. Now you can think about how you would map that to your thousands of chips that make up your accelerator system. You want to do so in a way that observes and is optimal for the communication patterns of the collectives, right? Forward passes, backward passes, etc. And the individual communication steps require tremendous amounts of bandwidth, very low latency. Now you can further imagine that you have a reconfigurable topology that you can co-optimize, such that once you decide how you want to do your mapping, the topology can be optimized to support that mapping, right? So it becomes an even more interesting optimization problem when you don't have a static topology.
Thanks a lot. So what are the main challenges ahead where, for example, on the higher layers of the networking stack?
Fault tolerance, I think, is one of the biggest ones, actually. And so now you can imagine that the kinds of communication that are taking place, let's stay focused on machine learning systems, are synchronous. And that means that among, again, thousands of elements, if you lose one element, you actually have to stop the computation. You have to go back to a checkpoint. So these systems are so long running that you can't just restart the computation from scratch. You have to actually be regularly taking a checkpoint. So one aspect here is how do you recover, how do you detect and recover from failures very, very quickly? So now we have our idealized view of what our topology looks like. But at the higher level of the network, as elements fail, you now have to remap the, let's say, model topology, your algorithm, to the hardware. If not in real time, then very quickly. Because at the scale of thousands or tens of thousands of elements, failures are taking place very regularly, maybe even at the granularity of minutes. You can't take many, many seconds, every few minutes, possibly every few minutes, to recover. So I think that higher level fault detection and fault recovery is very important. The other aspect of it, if you want to think about it moving up the network stack, is probably individual, what we call pods, you can call them clusters, whatever terminology you use, will not be big enough for our largest machine learning tasks. So in other words, we're going to have to bring multiple clusters, multiple pods together at the largest scale. You might have one network technology, super fast within a cluster or a pod. But then you might have more traditional, let's say, Ethernet, TCP, IP even, between clusters. Perhaps that's what it looks like. How do you coordinate between them at different granularities, and how do you ensure that you have, again, the right levels of latency and bandwidth, not to mention reliability, between clusters?
What about the implications on the routing system and congestion control?
So these are two classic problems in networking that will always be there. So again, we talked about this some. Congestion control has to happen at individual levels. The collective operations that are taking place in the networks today are very sensitive to tail latency. What this means is that it's not your average performance, your median performance that matters. It's the last, if you're trying to coordinate among 1,000 elements, and you have to wait for all 1,000, let's say, operations to complete. So what this means is that predictable congestion control is absolutely critical. In other words, you can't do really well 99.9% of the time. You have to do really well close to 100% of the time.
Yeah.
And now congestion control, again, is at various granularities. It could be in hardware. It could be on an individual packet basis. It, of course, could be in software all the way to the end hosts and elements that are managing the communication. Routing, we talked about some as well. I think that routing will continue to evolve. We've seen some of it already, from being a set of protocols that are focused on delivering connectivity to a set of protocols that can discover paths and instill sufficient forwarding states in individual switching elements to be able to ideally react in real time, maintaining connectivity, of course, but perhaps more importantly, maintaining application level SLOs. So one thing I'll mention with respect to congestion control and routing is SLOs, or service level objectives, talk about how we can ensure that we have target levels of loss, latency, and bandwidth from point A to point B. That's ideally what the application would like to think about. They don't want to think about congestion control or routing. They want to think about a logical pipe from point A to point B. It's then the partial job of routing and congestion control to meet those SLOs. For example, 99.99% of the time, I'm going to have this amount of bandwidth with this latency and this loss rate. That's the characteristic of the pipe, the logical pipe between point A and point B that I'm giving to the application. Right? And then lower level protocols like routing and congestion control, are in place to ensure that.
All right. I mean, there is so many, exciting more things to discuss, but we really want to thank you for taking the time and sharing your insight and perspective. That was extremely interesting. Thank you.
It's my pleasure. Thank you so much. Absolutely just a huge amount here, and it's one of the most exciting times in networking, no doubt.
Thanks so much, Amin.
Thank you.